Okay. Thank you, Caleb. Test 3, acid derivative chemistry. Test 3 and 4 will be on carbonyl compounds. Test 3, acid derivatives. Test 4, aldehydes and ketones. I put a video about the nomenclature of each of these on YouTube. It's one video. You watch half now for this test, and then watch the other half and get the test 4 material. Everybody get a green sheet? Handout for today. I sent 2 handouts for Friday that you need to have. You need to know your functional acid derivative functional groups. Some of them are highlighted here. And then the nomenclature for acids, esters, and amides shown on the back page. That's on the video. Let's begin today by looking at a topic: acidity of phenols and carboxylic acids. So check out the video see if you have any questions. We'll save about 15 minutes during each test period by doing the nomenclature on video. Okay, this is a good time to review some ideas about acidity and then basicity a little bit later. PKAs of some OH compounds, alcohol, about 16, like water. Phenols, we know are more acidic, about 10. This can vary depending on substituents on the ring. We'll talk about that. And then carboxylic acids, even more acidic, about 4 to 5. Benzoic acid, acetic acid. Why are phenols more acidic than regular alcohols? When this acts as an acid, it becomes an anion. It's localized. It's not delocalized. There's no resonance here. On the other hand, if phenol acts as an acid, we get the phenoxide. It is resonance stabilized. And we can draw resonance structures. Electrons down, electrons out, electrons down, electrons out. You can draw other resonance structures. You should be able to draw these resonance structures by now. So the anion is delocalized, so it's more willing to form. Why is the carboxylic acid more acidic than phenol? We get the anion. We can do resonance structure, electrons in, electrons up, given here. There's only one additional resonance structure. Where here, there's actually this one. There's 3 additional, other than the original. A lot of students think because there's 4 total resonance structures, this is more stable, and thus that's more acidic. That's not correct. This is actually more acidic. Why is this more acidic than this? We have the additional heteroatom. The charge is delocalized onto another oxygen. Where here, delocalization puts the charge on carbon. And carbon doesn't handle the minus charge as well. So these other 3 resonance structures do not contribute that much to the actual hybrid. Like another alcohol group here?
Yeah.
Why would that make it more acidic?
Never mind.
What were you thinking it would do?
Thinking another heteroatom for it to place on, but it doesn't work out.
No, you can't do resonance. There's no resonance. I mean, you do have electronegativity induction, which may stabilize the anion a touch. But there's no resonance there. We will talk about what type of groups you can put here. We need, this is like NAS, we need electron withdrawing groups here that we can move this into by using resonance. We'll get there. Okay, so carboxylic acids are more acidic because we're putting the anion We're delocalizing the anion over 2 oxygens. And of course, the hybrid looks like this, partial minus. These 2 bond lengths are the exact same because the 2 resonance structures are equal contributors. So something like acetate, the 2 carbon-oxygen bonds are the same length and you have the same amount of charge on each oxygen. Okay, as a result of the differences of acidity, we can talk about solubility of these 3 in aqueous hydroxide. Regular alcohols are not soluble in aqueous base. Aqueous base implies hydroxide. Hydroxide is not strong enough to deprotonate an alcohol fully. Now I'm talking about by deprotonation. Ethanol is actually soluble in aqueous base. But it's not because it's being deprotonated, it's because ethanol is just soluble in water, aqueous. So usually this refers to a larger alcohol that's not soluble in water. Phenol, on the other hand, and substituted phenols, etc., are soluble in sodium hydroxide because the hydroxide takes the H, leaves the electrons behind, and we get the phenoxide. I'll just draw O minus plus water. How do we judge this equilibrium? pKa of phenol 10, pKa of water 16. Which side's favored? The weaker acid, which is which side?
16.
This side's favored by how much? 10 to the 6. That's what, 1 million. So at equilibrium, you have 1 million of these and only 1 of these. It's pretty much done. I mean, it's 99.99% done. This being ionic will tend to be soluble in water. Where with the regular alcohol, we got 16 and 16. You may say, well, isn't half of it deprotonated? It actually just does not work out. Now, of course, carboxylic acids are also soluble in sodium hydroxide because this would be 4 and 16. That's overwhelmingly favored to make this the anion. Actually, with carboxylic acids, they're also soluble in bicarbonate, which is a weaker base. I'm not going to give you a PKA or anything. The carboxylic acids are soluble in bicarbonate where most phenols are not. Of course, you remember in your 3rd grade science project when you took vinegar and you added it to baking soda, and what happened? It formed. This took an H from this. This became carbonic acid. Carbonic acid is not stable. It broke down to water and CO2. The CO2 bubbled out, made your volcano. Okay, so that was a little review and background. Let's look at the effect of substituents on the acidity of phenols and benzoic acids, starting with phenols. Most of this will sort of go with our directing effects for EAS reactions that we just got through with. Ultimately, if you put a net donating group on the phenol, it's going to increase the pKa, which means it makes it less acidic. If you put a net withdrawing group on the ring, it will lower the pKa, thus this will make it more acidic. Well, that should make sense. If you're making an anion, how do you stabilize anions? You want something that will withdraw. So if you have a withdrawing group, it's going to stabilize the anion, thus making it more willing to form. You'll see the same trend for benzoic acids. Examples. Regular phenol is right at 10, maybe 9.9. Okay. If you put a methoxy on here, it goes to 10.2. So that means it's less acidic with this group there, yeah? Only slightly, but still that's the right direction. Why is it less acidic? This must be a net donating group. Well, what did we learn about such a group with EAS chemistry? It's a net donating group. What about this? This is paranitrophenol, 7.14. Much more acidic than just phenol. Okay? Why? Well, what do we know about nitro group on the ring? Strong electron withdrawing group net. Okay? So this should make sense. You actually put 3 nitro groups on the ring, the pKa goes down to 0.4. Now, 0.4, that's actually more acidic than a carboxylic acid. So you can't say that all phenols are less acidic. This is more acidic than a carboxylic acid. Why? 3 strong electron withdrawing groups really stabilizing the anion. This is so acidic it's called an acid. That's called a picric acid. Picric acids actually are explosive. If you replace that OH with a methyl, what would you have? You would have trinitrotoluene. Yes. Trinitrophenol is also explosive. A lot of times you will see picric salts. Picric salts are hazardous. Interesting. Compare these two. Which one is more acidic?
Para.
Yes, para. Why is it more acidic than that one?
Almost in the right position.
Like over 10 times more acidic.
It's the right position for resonance. Orthon error resonance. It's in the right position for resonance.
If we consider the anion, let's not put any groups there yet, and we do resonance structures, like was shown up there. Actually, why don't we go ahead and just move right back up there and show the rest of it. There's one, electrons here, electrons out. We can get there. Electrons here. Okay, that's a single bond. We're moving in to make pi bond. Move that pi bond out. So we get these resonance structures. Where does the minus fall compared to the original oxygen? Ortho, para, ortho. So if you put an electron withdrawing group on the ring, where do you want to put it to have the greatest effect? Ortho, para. If you put it meta, it's not going to have as much of an effect. Now it still will have some effect because it's still a withdrawing group. It won't have as much. For example, let's pretend all these have a nitro on them. Okay, let's throw in a nitro, which is a dipolar functional group. Okay, if there was a nitro para, we could draw an additional resonance structure where we move these in and these out. And that would give boom, boom. And now we have boom, boom. And we can delocalize the charge onto another oxygen. Yes, there's 3 charges here. You can't get away from the original 2 with the nitro group. You can only do this if the nitro group is where the anion falls. If the nitro group is at the meta position, you would never be able to draw this extra resonance structure. So here the nitro withdraws by resonance. If it was at the meta position, you would say it only withdraws inductively. So that's why this guy is 10 times more acidic than this guy. That's why these being all in the correct positions, very acidic for a phenol. Okay, let's look at benzoic acids. The same type of trend holds there. We see R here and then define R in our table. Benzoic acid itself is 4.2. If this is a bromine, it goes down to 4.0, so it's getting more acidic. Why? What's the net effect of a bromine on the ring? It's group 3. Okay. And when we're talking about net effects here, we're talking about the EAS effect. Yes, bromine is a net withdrawer. Okay, that's going to pull electrons away from the ring, away from here, make it more acidic. If this is a methoxy, though, it's not more acidic than with the H. It's actually less acidic. Because we know methoxy actually donates electrons into the ring. Okay? Or does it? Look at this example over here. Here the methoxy is para. If the methoxy is meta, here's your PKA. Compare that to H. Is this more acidic or less than if... It's more acidic with the methoxy in the meta position. But in the para position, it's less acidic. Explain this one. That's really your role, right? You guys are lawyers, okay? You've got to learn how to explain and make an argument. What's your argument for that one being more acidic? If I said induction, explain further, Counselor. Do what? Why would this pull electron? It pulls it by induction? I can't hear you. A little. What's induction? Induction is based on what? That's moving electrons through single bonds. That's based on what? Electronegativity. Is oxygen more electronegative than carbon? Yes. Okay. Pulls by induction. But what can oxygen also do? It can donate by resonance. Ultimately, the donation is more of a factor here by resonance, where here resonance is not as important, but here the induction is actually more important. See, oxygen is schizophrenic. It donates by resonance, but at the same time it pulls by induction. Now we said with the AES, the donation by resonance is a major effect. And that holds here. But here, apparently it's not. I remember telling us that this is a net donating group in this case. The reason being is, if we make this O-methyl here, and start drawing resonance structures, I'm going to ask you to draw these on your own. But you can get to a resonance structure these electrons, you can show them resonating all the way into that carbonyl over there. You should be able to get here on your own. You go sit down and Each step, boom, boom, boom. Before you know it, you move the charge here, plus here. Okay? In the pair position, it does that. Guess what? It also does this in the ortho position. But in the meta position, you can never draw a resonance structure using these long pairs and move them onto that oxygen. It's not going to ever occur if you sit down and do your resonance structure. You should sit down and try to do it. Okay? So the resonance effect is, yes, it's felt in the ring, but it's never felt onto the carbonyl. And apparently, why do we say apparently? Because there's the number. There's the fact right there. Apparently, the withdrawing of the oxygen is the predominant effect with the meta-methoxy. And while we're here, let me add something. I don't think it's written here. It may be on the next page and I didn't quite see it. These PKA values are stone cold facts, evidence. And you can learn about groups by determining the PKA. For example, what if this was, I've already got a structure. What if R was HgCl? That is, we had HgCl. Mercury is usually divalent when it's covalent. Okay? Is this a net withdrawal or donating? There's probably lone pairs there, but it's also more of a metal, which is more tends to be electropositive. Okay? You don't know. How could you tell?
Okay, you can.
Yeah, you could go determine the PKA. What if you go determine the PKA, and the PKA of this is 4.4?
Donated.
Yes, that means that the group must be an electron donating group net.
That's because it's higher than the H, if it were...
Right, it's higher and thus it's less acidic. That implies that this must be a donating group. That would make it less acidic. If it was a withdrawing group, you would expect pK to be lower than the H. So you can use PKAs to tell you about groups. That make sense? Okay, let's look at acidity of aliphatic carboxylic acid. What does aliphatic mean?
Non-aromatic.
That means non-aromatic, but more precisely it means it means saturated. Aliphatic is an old term for saturated. Now, of course, your carbonyl is a degree of unsaturation. But what it means is the remainder of your molecule is all saturated. Olefinic means double bonds present. Aromatic, of course, the aromatic ring. Saturated and aliphatic pretty much means the same thing. But that's just a portion other than your functional group. Okay, acetic acid, 4.76. Chloroacetic acid, you put chlorine here, more acidic. Why? We've got this electron withdrawing group, inductive withdrawer. It will stabilize. Remember in organic 1, we were really looking at the anion here. How likely is the anion to form? Well, this anion is going to be stabilized by the chlorine pooling, so the anion is more likely to form. You put 2 chlorines, what is that, 1.29? You put 3 chlorines, 0.65. So as you add chlorines, more withdrawing, stabilizing the oxygen anion.
Can you see terminology like group 3, or is that the aromatic compound?
Well, group 3 was EAS.
Okay.
We'll get to more about that in just a minute, I think. There's a big difference between what we were doing with EAS versus this here. Okay. The closeness of the halogen to where the anion is going to form is important. The closer it is, the greater effect. As the chlorine moves away, the effect is not as strong. This is still more acidic than this, but it's not as acidic as if the chlorine is closer. So the effect sort of tails away. How about this guy? Would you expect it to be, compared to this, more acidic or less acidic?
More or less.
You'd expect it to be less acidic than the chlorine. Why? Chlorine, iodine is less electronegative. It doesn't pull as much. So that's your trend for your halogens. Which halogen is going to give you the greatest effect? Chlorine. Fluorine. And actually, trifluoroacetic acid has a pKa of less than 0. Okay? And trifluoroacetic acid is a pretty strong acid. Okay, how about the guy below? Compare this to this guy. Or actually, let's compare it to, I think it'd be better to compare it to acetic acid. Acetic acid or this? Which one's more acidic?
Acetic acid.
What'd you say? Which one's more acidic? This one or acetic acid?
Acetic acid.
I heard some say acetic acid. Anybody say this is more acidic? Yes, she did, right there. I saw it. She flexed. Remember when you're like at an auction and you sort of do this, they're like, we got 500 right here. Yes, this is more acidic. More acidic than that, right? Right, why? Why is this more acidic, Shelby? It's because I don't know how you would do that. Well, of course, any carboxylic acid, you can put the charge over here by resonance.
That donates by induction, not by resonance.
This is what?
That donates by induction, not by resonance.
Both by induction.
Yeah,
Donates by induction?
No, withdraws by induction.
Oh yeah, it withdraws by induction. Oxygen is more electronegative than carbon. And if it withdraws, that's going to make it more acidic than this, which doesn't have a withdrawing group. Makes it more acidic, right? So why did you all either not vote or say it's going to be less acidic?
Red didn't contribute to resonance.
You're saying this contributes resonance?
I said if it, so I can't, but if it is.
Well, if is a big word. If I had, a kilogram of gold, it'd be all right. This cannot donate by resonance. Is this doing any resonance over here? There's no p orbital here. There's no resonance here. Okay? What I'm getting at is, see, this is different than EAS. With EAS, it had potential to withdraw and do resonance because of those pi bonds that we're conjugated with. There's no resonance here of this group. You cannot draw any resonance structure of this lone pair. There's no p orbital here. All this thing is doing is withdrawing inductively. That's all it can do. It can't do both. And if it withdraws, it makes it more acidic. So this is an example of, you can't just say, oh, methoxy, it's in the withdrawing group. No. In EAS it is. That make sense? Okay. Over here is pretty much what we just did. Okay? That's what we just did with those examples. Questions before we move to basicity of anilines? Okay, let's look at basicity of anilines. Aniline here, pK of 4.6. So aniline is not an acid. I mean, it can be an acid, but the pK is not going to be 4.6. This implies a pretty strong acid. Okay? If this is going to act as an acid, that pK is about 30. Typically, anilines are going to be acting as bases. So give a PKA. What does this refer to? Conjugate acid. Okay, PKB would be 14 minus 4.6, was it 9.4? But I don't know what a PKB is. Okay. Refers to the conjugate acid. Refers to this. Now, the more acidic this is, the less basic the aniline is. So, if this pKa goes down to like 3, does that mean the aniline is more basic or less basic? It means it would be less basic. Because if the pK goes down to 3, that means that the conjugate acid is more acidic. Thus, correspondingly, the conjugate base is less basic. So you got to make sure you know what your numbers mean when the pKa of the base changes. Okay? So that's that. Now, compare aniline. By the way, aniline. Aniline is the exception. This lone pair is in what type of orbital? It's in a p orbital. And we've always kind of said that if a lone pair is in a p orbital, it's going to be non-basic. It's typically true. Aniline is actually sort of the exception. It's a fairly weak base. But it does have some basicity. Because if you try to do resonance and delocalize this lone pair, what type of atom are you putting the lone pair on? Carbon. See, carbon doesn't like lone pairs as much. So it's not fully delocalized. It is somewhat localized on that nitrogen, even though it is in a p orbital. So it does have some slight basicity. Now, but of course, this does affect the basicity. Still very light, low. How about this guy? First off, you expect it to be more basic or less basic?
More basic.
Yes, this is more basic than aniline. The lone pair is in what type of orbital? Lone pair is in an sp3. It's an sp3 nitrogen. It only has sp3 orbitals. Okay? That is going to be a pretty good base. Now, it's not as strong as like hydroxide because this is a neutral molecule. But of the neutral molecules, this is one of the most basic of neutral molecules. sp3 nitrogens is actually often called sort of nature's bases. Because most of the bases you find in nature are like sp3 nitrogen. Neutral compounds. Let's look at the anilines though. By the way, what is the pKa for this aliphatic amine or this saturated amine, primary saturated amine? Approximate pKa. Is it going to be higher or lower than M?
Higher.
Higher.
Yes, good. It's about 10. Hydroxide is about 16. So hydroxide pKa really refers to the conjugate acid, which is water, 16, right? Okay? So it's not as basic as hydroxide. It's more basic than... yeah. By the way, I can give you another pKa. How about this? What do you call that? Pyridine. What type of orbital is this lone pair in? Yes. More basic or less basic than this?
Less basic.
Less basic. Hybridization effect. More S character, holds it lone pair tighter. Less basic. That one's hard to include relatively. But this is a pKa. Is it going to be higher or lower than that? Lower. It's about 5. It's actually pretty similar to aniline, maybe a little bit more basic. Not as basic as this guy. Okay, let's look at anilines and the effect of substituents on the benzene ring. It's going to be similar to what we saw earlier. If you have an electron withdrawing group, that will make it less basic. It's less basic. Because if this is pulling electrons, that's going to decrease the electron density on the nitrogen, making it less basic. Lower pKa. If you have a net donating group, that's going to make it more basic. So we can look at these over here. Which one of these two is more basic?
Right.
Yes, that's more basic, and this is less basic compared to aniline itself. Now you may be wondering, what if we put this in the meta position? Actually, I don't know. Just because it's in the meta doesn't make it going to be withdrawing group. Certainly, probably not going to be as basic as this guy. But sometimes the exceptions are not so much a rule. It's just, this is a specific, isolated exception. That should make sense based on your EAS knowledge of groups on rings. Yay? I've already mentioned this at the bottom. Aniline, of course, can be an acid. For example, this acts as an acid, it becomes this. The pKa for that is about 30. Okay? You rarely ever see aniline act as an acid. But of course it can. For example, if you react with n-butyl lithium, the carbanion will take an H from aniline. Okay. Let's do a review of our extraction process. We covered this in Organic 1. Of course, as our knowledge has increased, we can go back and review it. Maybe it will sink in a little bit more. Make sense a wee bit more. We can often take advantage of acid-base properties to separate compounds using an extraction process, separatory funnel, etc. How could you separate these 4 compounds by an acid-base extraction process? Well, we want to assess them. Is one acidic, basic, or neutral? Acidic. This guy.
Basic. Or no, neutral.
Try again. But no. Acidic. But not as acidic as that. Aniline. Basic. Slightly basic. That's naphthalene. Be neutral. You're not going to remove an H or add an H under aqueous conditions. The extraction is aqueous conditions. Okay. The strongest base you can have under aqueous conditions is hydroxide. Okay. How would you separate these? You can read through all of this. I'll take you through it and give you the summary. Okay. Essentially, like we talked about in Organic 1, under what if we can convert some of these to an ion, the ion will then usually preferentially go into the water layer. 4, can you convert it to an ion by acid or base? No, we call it neutral, okay? 3, can you convert it into an ion?
Yes.
Do you want to use acid or base?
Acid.
Acid will convert this into the protonated nitrogen cation. Okay? You got to know your fundamental acid-base reaction. If you can't already envision or show the ion, you need to sit down and do a little review. Okay. First off, you would dissolve these in some type of organic solvent. What's your favorite organic solvent for extraction?
GMSO.
DMSO would not be good because we're going to mix it with water. Okay? And doing extraction, you want 2 separate layers. So you want to use an organic solvent that's not miscible with water. DMSO and water mix completely. You'll only have 1 layer. Diethyl ether. Dimethyl ether is a gas. It would be hard to extract with a gas. You might could. Diethyl ether is a gas on a July hot day. If it's real hot. So you need okay, if you look back at the solvent list I gave you at the beginning of Organic 1, I separated them into water-soluble and non-water soluble. Ethyl acetate is a good extraction solvent. Dichloromethane, diethyl ether. If your compounds are highly soluble, you can use something like hexane. The problem with hexane is a lot of organics are insoluble in hexane because it's so dang nonpolar. That would be soluble in hexane, but these 3 probably would not be, even in the neutral state. Okay, so sometimes you dissolve these in diethyl ether. Then add in some acid. Shake it up. Chemistry will take place. Which one of these will be converted to an ion with acid? Number 3, it will go into the water layer, the acid water layer. 1, 2, and 4 will not. They'll stay into the organic layer because you cannot convert them to ions with acid. Okay? Separate your layers. This is in your water layer. Only 3 remain in the organic layer. Now you can take your water layer and basify it. That will remove the proton and you get back your neutral form. So that's separated. Now we got 1, 2, and 4 into ether. Now we treat it with base. What base you want to use? You want to use bicarbonate? If you use bicarbonate, bicarbonate will deprotonate which one?
1.
Only 1. Remember we said bicarbonate will only deprotonate a carboxylic acid. Bicarbonate will deprotonate this and make that go into the aqueous layer. These 2 will not. Separate your aqueous layer. You can then acidify it, put the proton back on, and that one separated. Then how would you separate 2 and 4? You use hydroxide to get this one to become anion. So shake it up with hydroxide, let the layers separate, drain off your hydroxide, which contains only this. Got it separate. You can acidify it with a strong acid, put the proton back on. A lot of times when you acidify these back, this may precipitate as a neutral form. And you can collect it by suction, each individually. Number 4 will always remain in the ether layer. when it's the only one left, you can just take your ether and rotovap it off, and then you'll have number 4 in your flask. You can read through it. I gave you sort of my talking summary. Hopefully that makes a little bit more sense than when you saw it in Organic 1. Now they may have done it a little bit differently in terms of bicarbonate versus hydroxide. Okay, we got 5 minutes left, and I wish I'd brought the next handout to at least show you. You may not have it today. Anybody have the handout that I sent by email? Maybe, can I see it? Maybe I want to show you just an overview of some things. I think the stuff here, we're not really kind of looking at those miscellaneous examples yet. Thank you. Okay, guys, you may not have this here today. Let me just give you an overview so you can be ready for Friday. One of these is the outline, chemistry of acid derivatives. There's your chapters in your textbook. We'll start with synthesis of carboxylic acids. A couple of the methods will be reviewed. For example, during test 2, we saw how to make a benzoic acid. Okay? And there will be a couple of new methods. Synthesis, then we'll go to reactions of carboxylic acids. We'll synthesize each functional group, and then we'll look at the chemistry of each functional group. So there's your outline there. And the other is sort of a written handout. I begin with sort of a interconversion. All of your acid derivatives can be converted from one to another, and that's called interconversion. All right? The king of your acid derivatives is the carboxylic acid. That's why everything else is called a carboxylic acid derivative. Here's your ester. This is probably amides, nitriles. 2 functional groups that are not on the opening drug page of the other handout. Acid chlorides, but we've seen acid chlorides before, used in the Friedel-Crafts acylation. This is an anhydride. Anhydride. We'll learn about them. We'll learn. Please look at how this is organized, as written here, reactivity. This sheet, as we go along, I want you to put on each arrow the reagents that are needed. For example, what reagents would convert this to this? Put it here. So it's sort of a summary page where you can take what we've done in class and go back and say, okay, summarize it. You summarize it. Please look at like the mechanism. Basically, please be prepared to go over this stuff on Friday. We got like maybe a minute. Let's think about lab. From the iodo, the next reaction is the Suzuki reaction, using a boronic acid. That reaction shared the Nobel Prize in 2010, uses a palladium catalyst. It's a very modern reaction. It's really changed organic synthesis in the past 25 years. If you have enough iodo, you can proceed to do that reaction. Who did not get enough iodo to do that reaction? Okay. That means how much iodo did you get? Like less than 100 milligrams? Or just a trace?
That's true. Enough for melting point.
Okay, enough for melting point IR dust. Okay, I set a procedure to make the iodo directly from chlorine, so you don't have to use your amine. And directly from chlorine, it may be a little bit better yield. Although I've been doing the diazonium myself in the lab, and getting pretty decent yield. And trying to look at some of these reactions. We developed them all originally, but sometimes they can always be improved. Okay, so you can do maybe the Suzuki. Imine, reacting the amine with an aldehyde. Basically, you should know what you're doing. I continue to see caps left off for reagents last week, after I asked you not to do this. I continue to see balance areas. I don't know why, it looks like compounds are weighed out and just left there. Please need to have a little bit better hygiene in lab. Okay? Any questions about lab? Shelby?
Do we more round bottom left for,
Unfortunately, we do not. I'm going to have to just make the best of it. Like, what do you need?
just because if we have to do 2 reactions this week to get more iodo and to stay on track?
Well, you also only have 1 hot plate, 1 condenser. So you can put one on to reflux, and then maybe you can be melting point IR, or you can do like a column for something. You can find something else to do. Run TLCs while something's refluxing. You can find something to do. In terms of efficiency, I do see some of you sort of just standing there watching it reflux. Day 8's going to be here, and you're going to have a lot to do. You need to be working efficiently. While something's going on, you need to be doing something else. Larry?
NMRs.
Good. I need to get the NMRs out. I'll pass them out, but I need to go ahead and do that so you can start picking them up. I'll probably put them in the IR room on like those black tables, and you go in there and you get the compounds you need. Everybody will need to get the nitro and the amino. When there's variability, like in your halogen, you need to make sure you get the right NMR. I'll probably send an email about this. I need to set them out. Thank you for the reminder.
I take it we're not going to be using the NMR machines at all this term?
Yeah, because we got a brand new NMR. I haven't even hardly used it.
Okay.
And the older one is not operational right now. We can take a look at the NMR if you like. Okay, see you soon, guys.